Thanks for the nice introduction. So today my talk is about the decentralized complexity. Here's the outline of my talk. First, I will introduce the model, and then I will focus on three different topics in decentralized complexity. The first is the decentralized complexity of graph properties and the evasiveness conjecture. The second topic is two different measures, the sensitivity complexity, block sensitivity, and the sensitivity block sensitivity conjecture. The third part is about another different measure, the degree complexity and the related conjectures. So let's first start from the model. Decentralized is a widely used model. For example, in machine learning, we would like to classify different data. And this procedure can be written down as a decentralized like this. Actually, in the algorithm 101 course, the sorting algorithm can be represented as a decentralized. Using this representation, we can actually prove any comparison sorting algorithm to sort n element will need n log n lower bound. The reason is that there are in total n factorial different orders. Therefore, the decentralized must have n factorial leaves. So the depth of the decentralized is at least n log n. So here's the formal definition of decentralized. Let's simplify that we only focus on Boolean functions in this talk. So all the variables are 0 or 1, and the value of the function is also 0 or 1. We would like to know the value of fx by asking queries, what is xi? And this procedure is adaptive. That means after query x5, for example, and according to the value is 0 or 1, we may query different variables. And the complexity is measured as the worst case, the depth of the tree. And for a function f, the decentralized complexity is defined as the minimal over all decentralized which can compute this function. According to the model we use is deterministic or randomized or even quantum, we have different notations. df means the deterministic decentralized complexity. rf represents the randomized decentralized, and qf for the quantum. It's clear that the decentralized complexity is always less than or equal n, because if we query all the variables, then definitely we know the value of fx. And a function f is called evasive if the decentralized complexity is n. That means, in some sense, the function is hard to compute. On the opposite, we know that, for example, for the constant function, the decentralized complexity is 0, but that function is some sense trivial. And we also have some non-trivial function. The decentralized complexity is also small. For example, the dictator function. This function is only related on few variables. So a natural question is, how low can the decentralized complexity be for non-degenerate function? That means the function depends on all the variables. Here's a warm-up exercise. We can prove that for any non-degenerate function, the deterministic decentralized complexity is at least log n. This is because if the function depends on the variables, then every variable must appear in somewhere in this tree. Therefore, again, this tree will have at least n leaves, so the depth is at least log n, very similar to the proof of the sorting lower bound. And actually, this log n bound is tight. There's a famous function called the address function. It has n plus 2 to the n different variables. the first n variable are the index, and the last 2 to the n variables are the value of this function. And up to a log n additive term, this bound log n is tight. And if we restrict function to be monotone, still log n is the tight bound. Okay, let's move to a special type of functions, the symmetric function. A function is called symmetric if we permute all the variables, the function keeps unchanged. In other words, this function only depends on the summation of all the xi, the weight of the input. And another warm-up exercise shows that for any non-trivial symmetric function, that means the function isn't a constant, it's evasive. That means we need to query all the variables. The proof can be done by an adversary argument. Since the function is non-trivial and symmetric, there must exist a k such that the weight n minus k input at the value is different from the weight n minus k minus 1 input. And when the algorithm queries all the variables, the adversary answers the first n minus 1 bit like 0 to the k and 1 to the n minus k minus 1. Then this will force the algorithm to query the last bit. A widely studied and important extension of symmetric function is the weakly symmetric function or transitive invariant function. A function is called weakly symmetric if there's a transitive group G such that the function is invariant under G's action. That means we act G on all the variables. For example, permanent function, determinant function, are weakly symmetric because if we permute the rows or permute over the columns, the function is invariant. The invariant group is s square root of n times s square root of n. An even simpler function is the cyclic invariant function. So the invariant group is the cyclic group Cn. If we shift the variables, the function keeps unchanged. A natural question is, for weakly symmetric function, is it always evasive? The answer is no. Actually, we can prove that for any non-trivial weakly symmetric function, the decentrate complexity is at least square root of n, and this bound is tight. I will give an example in exercise. An important special case of weakly symmetric function is called graph property. So there are n-2 variables. So basically each edge is a variable. If there's an edge between vi and vj, then the variable xij equals 1. Otherwise, xij equals 0. And we call a function a graph property if we permute the vertex, the property keeps unchanged. For example, the connectivity, bipartiteness, triangle free, planar, three coloring, basically all the intrinsic property of graph is a graph property. And for the connectivity property, we can prove it using the adversary method that it is evasive. This was first proved by Bolabas, and the following proof are from Lovaz. It's still an adversary method. And the strategy is that when we query whether there's an edge between I and j, the adversary always answers 0 unless the answer will imply the graph disconnected. That means among the unqueried edges plus the edges that the answer is yes, there always a spanning tree. We always maintain a spanning tree among them. And therefore, if the function is not evasive, that means there's one edge at least that doesn't query it. This will contradict to the descent tree because there will be n edges there. There must be a cycle. And use different adversary strategies. We can also prove that triangle-free, three-colorable, and many other graph properties are evasive. And Rosenberg conjectures that actually for any non-trivial graph property, the descent tree complexity is always omega n squared. And Anderer gave a example for this conjecture. He constructed a graph property called scoping. For this graph property, the descent tree complexity is only On. And also this gives the example for weakly symmetric function. The upper bound square root of capital N is tight. Because here in graph property, the capital N is n choose 2, n square order. Here's the scoping property. So there's one node called the body has degree n minus 2. The only vertex not connected to the body is called the sting. And between them are the tail. And there are n minus 3 vertex which connect to the body. The edges among them are arbitrary. Okay. And it can be shown that for this property, we can use only 4n or 5n queries. And later, Anderer refined Rosenberg's conjecture, and now it's called the Anderer-Rosenberg conjecture. They put the monotone constraint to the statement. That is, for any non-trivial monotone graph property, the descent tree complexity is at least omega n squared. By monotone, here I mean it's bitwise. That means if x less than y, that means for any xi is less than yi. And many graph properties are monotone. For example, the connectivity, the bicoordinates, the triangle-free planar. If we add edges or we delete edges, the property keep unchanged. Notice that scoping is not a monotone property. And first, Karp further refined this conjecture to be the Anderer-Karp-Rosenberg conjecture, or now we also call it the evasiveness conjecture. He claimed that actually for this non-trivial monotone graph property, it's evasive. That means we need to query all the n choose 2 edges. And the previous Anderer-Rosenberg conjecture, we also call it the weak version of evasiveness conjecture. And here's the history of this conjecture. In 1976, Rivest and Vellemin proved that for any non-trivial monotone graph property, the determinate query complexity is at least n squared over 16. And this result confirmed the weak version of evasiveness conjecture. In their proof, they proposed a new method instead of the adversary method. They call it algebraic approach. I will explain this in the next slides. And later, this bound was improved to n squared over 9. And in 1984, King, Sack, and Statement proved that the descent tree complexity is at least n squared over 4 plus a little term. And more important, in their proof, they propose a new method called the topological approach. I will also explain it in next few slides. And using this topological approach, Andy Yao in 1988 proved that any non-trivial monotone bipartite graph property is evasive. By bipartite graph properties, that means if we permute the left part or we permute the left part of the graph, the property keeps on changing. And currently, the best lower bound for the evasiveness conjecture is n squared over 3. Still, there's factor 3 there. Okay, let me briefly introduce the algebraic approach by Rivest and Willeming. First, they associated a polynomial capital Fc to each Boolean function f. It's a one-variable polynomial and defined as the summation over fa times the z to the 8th power. And an important observation from Rivest and Willeming is that 1 plus z to the power n minus the df always a factor of this polynomial. That means if we can show that fz do not have a factor 1 plus z, then that means df must equals to n. The function must be evasive. And an even simpler case, when we put z equals 1, we can show that 2 to the n minus df always a factor of the summation of fx. Therefore, if the summation is an odd number, that means the function has odd value 1, then that means it cannot divide by 2. Then that function must be evasive. And also we can put that to be minus 1. A corollary that the function, if it is not evasive, then f minus 1 should be always 0. This can be shown, the lemma can be proved by a mathematical induction along all the passes. So I will skip this part. And using this corollary, Rivest and Willeming are able to show that when n is a prime power, then every weakly symmetric function, notice that here it's about weakly symmetric function, not graph property. And also the function, if satisfy f0 not equals f1, then it must be evasive. The idea basically is when n is a prime power, p to the k, then all the orbit, the number of input on that orbit should be a multiple of p, except the case all 0 and all 1. And if these two values are not 0, then we can show that f minus 1 modulo p is not 0. Therefore, f minus 1 isn't 0. That means the function is evasive. And for monotone graph property, it's clear that the all 0 and all 1, the values are different. And the only thing is that we need to embed this weakly symmetric function into that graph. And using 3 steps, Rivest and Willeming are able to show that. And this is also why the n squared over 16, the 16 comes from. And we can consider each input as a subset of 1 to n. If we collect all the input, the value is 0, then it forms a complex. And for monotone function, this is a sequential complex. And a key observation from Ken, Sachs, and Sutherland is that if this function is non-evasive, then this sequential complex is contractible. That means it can continue shrink to 1 point. And they further notice that if phi is a one-to-one sequential mapping on this complex, then the Eulerian characteristic of the associated fixed point complex is -1. And combine this, and also since the function is a graph property, is invariant under the permutation of vertex, they can show that when n is a prime power, the Eulerian characteristics, the value is not -1, and therefore the function is not evasive. Here's the open problem for this part. The first and the most important open problem is, of course, to prove the evasiveness conjecture. As I said, there's still a factor 3 gap there. And besides the deterministic version, there's also the randomized version evasiveness conjecture proposed by Karp and Yao, although Karp denied of this. And this conjecture asserts that for every non-trivial monotone graph property, the randomized query complexity is omega n squared. So basically, using randomized algorithm, we can save a factor, for example, like a 2 factor, but that's the most we can do. And in 1987, Andy first broke the omega n barrier. He showed that the randomized decentralized complexity is at least n times log n to the 1/12 power. Later, King improved this to the n to the 5/4. And currently, the best is from Hardinal and Krakovsky and note that the bound is n to the 4/3, basically. That's a huge gap between n squared and n to the 4/3. Also, there's a quantum version of evasiveness conjecture proposed by Baumann, Cleve, de Wolf, and Zaka. It asserts that for every non-trivial monotone graph property, the quantum decentralized complexity is at least omega n. Because we know that if we use Grover search for the complete graph property, a Grover search will give a ON upper bound. Therefore, omega n is the best we can hope. And in their paper, Baumann et al. Shows that the quantum query complexity is at least omega root n. Here n is the number of vertices. So that means for the input size capital N, this is n to the 1/4. And later, together with Andy and Shengyu Zhang, actually we show that the monotone constraint can be removed. That means for every non-trivial graph property, the quantum query complexity is at least omega root n. And also this bound root n is tight. We show that for the scoping property, which was mentioned before, there's a quantum algorithm can only query square root of n. Here, the tilde means that I hide some polylog factor here. And in a private communication with microsensor, Andy proved that for monotone graph property, the quantum decentralized complexity is at least omega n to the 2/3. And very, very recently, Scott Arson, Ben David, Kossi, and Avisha et al. Finally proved this conjecture. And their proof is based on a recently breakthrough by Hao Huang on the sensitivity conjecture, which is the next topic of my talk. So before I move to the sensitivity part, I would like to mention another direction for evasiveness conjecture, the hypergraph version. proposed by Babai. So the statement of this conjecture says that for every non-trivial monotone, hypergraph property is evasive. For example, for the K-uniform hypergraph property, the deterministic decentrate complexity conjecture to be n choose K. And together with Kukari and Qiao, we proved a weak version of this conjecture for 3 uniform monotone hypergraph properties. An interesting thing is that in our proof, we combine both the algebraic approach by Rivas and Bellarmine and also the topological approach by Kahn et al. Very recently, Black was able to prove the weak version of this conjecture for any constant K. The approach he used is similar to our approach. Okay, let me move to the second topic, the sensitivity conjecture. Sensitivity was first proposed by Stephen Cook. So for any Boolean functions, the sensitivity of this function on input x is defined as the index I, such that if we flip the ith bit, by flip I mean change 0 to 1 or change 1 to 0, the function value will changes. And the 0 sensitivity or the 1 sensitivity is defined as the maximum over all the input with value 0 or value 1. And the sensitivity of this function is the maximum of x0 and x1. And actually, you can also consider this as a combinatorial coloring problem. So any Boolean function can be considered as a Boolean hypercube, and the value 0 and 1 can be considered as a two coloring, blue or red. And then the sensitivity of this function on a particular input x is just how many neighbors of x has different color with x. And the block sensitivity proposed by Some in 1989 is a natural generalization of sensitivity. So here, you are allowed to flip not only a bit, but a block. But the constraint is that these blocks are disjoint. Therefore, the block sensitivity of this function on an input x is defined as the maximum number of blocks, such that there exists disjoint block. We flip each block, the function value will changes. And we can also define the 0 block sensitivity and the 1 block sensitivity, and also the block sensitivity of this function. From this definition, it's clear the block sensitivity on any input is always larger than the sensitivity of that input, because sensitivity is a special case. We restrict each block has size 1. Therefore, the block sensitivity of the function is always larger or greater than the sensitivity. Okay, the certificate complexity. Or you can consider it as a non-deterministic decentrate complexity. So a 0 or 1 certificate of this function is a partial assignment of the variables, such that if the input is consistent with this partial assignment, then the value is 0 or 1. Okay, just like the NP and co-NP. And similarly, we can define the certificate complexity as the maximum over C0 and C1. Okay, and again, from this definition, we know that the certificate complexity is always larger than block sensitivity. This is because if we want to change the value by flip a block, then this block must contain at least 1 certificate index. Otherwise, the function value will not change. Okay, the last definition, the polynomial degree over reals for a Boolean function. So any Boolean function, we can represent it as a multilinear polynomial because we are on the Boolean domain. Therefore, x squared always equals x for each xi. And the degree of this multilinear polynomial is defined as the degree f. For example, for AND function, the polynomial is x1 times x2 times xn. The degree is n. And for all functions, the degree is also n. And here's the polynomial. And from the definition, we can show that the decision tree complexity is always larger or equal to the degree. This can be shown from the decision tree. From the decision tree, we can write down the polynomial. And let me list all the measures we already defined here: the DF, IF, QF, and the certificate, block sensitivity, and the degree. And by definition, we have some inequalities. And also we can show, I think first maybe prove by Lovatz in his select notes that the CF square is always larger than DF. Okay, we have the opposite direction. And also between C and BS, Some shows that BS square larger than C. And Some and Segedi shows that the degree and BS, there's a quadratic, at most quadratic gap. And Bowman et al. Shows that the square of quantum coherent complexity is larger than BS. So basically, for this part, all the measures in this block are polynomially related. By polynomially related, I mean for two different measures A and B, B is always bounded by a polynomial of A. Since DF is largest among them, so we can always compare a measurement with B, D. Here list some of them. And the only exception here is the sensitivity. We only know one direction. The sensitivity is always no more than the block sensitivity. However, we don't know whether the block sensitivity can be upper bounded by a polynomial of the sensitivity. This is the sensitivity conjecture. By the way, a nice survey by Bowman and Wolf in 2 summarize all this inequality here. Okay, so the sensitivity conjecture was proposed by Some and Segedi in 1992. It asserts that for any total Boolean function, the block sensitivity is upper bounded by a polynomial of sensitivity. Actually, in 1988, in different literature, Van Chong et al. Proposed a similar conjecture. Their focus is a graph problem. So the statement of the conjecture says that any induced subgraph of the Boolean hypercube of size at least 2 to the n-1 plus 1, the size means the number of vertices. Then there must exist a vertex of degree n to some constant. The conjecture actually, the degree is actually root n. And Guzman and Lino later shows that this conjecture is equivalent to the following. The degree complexity is upper bounded a polynomial of the sensitivity. And combine a result of Some and Segedi that degree always larger than the square root of block sensitivity, and also the degree is upper bounded by the block sensitivity to the cubic. Then Van Chong's conjecture up to a polynomial is equivalent to the sensitivity conjecture. Okay, here's the previous known result about sensitivity conjecture. Simon in 1983 proved that the block sensitivity is upper bounded by 4 to the sensitivity power times sensitivity. Actually, what he showed is that for any degenerate function, a lower bound for sensitivity, and we can convert to this inequality. 20 years later, Keon and Cutting improved this 4 to the s to e to the s, with also some little terms. And again, 10 years later, Ambanis, Bevening, Yihan Gao, Jieming Mao, me, and Song Zuo, we prove that actually the certificate complexity is upper bounded by 2 to the SF, basically. Since the block sensitivity is always no more than the certificate, this improves the previous result from E to the 2. 2 years later, Ambani's process will further improve a little term, a 1/3 2 to the s. And together with Kunhe and Qianli, we further improve the factor of the leading term from 1 to 8/9. By the way, Kunhe will give a talk on Thursday morning. And still the upper bound is exponential, so it seems far away to prove the conjecture. Before I mention how Huang's breakthrough, let me briefly mention about the lower bound. By lower bound, I mean the gap between SF and BSF. In 1995, Rubinstein showed that there exists a Boolean function. The block sensitivity is 1/2 times the square of sensitivity. That means if the sensitivity conjecture is true for some constant C, then the constant is at least 2. And later, words are improved by a little term, 1/2 SF. And together with Ambanis, we further improve the leading factor from 1/2 to 2/3. And this is the largest gap currently we know, but still quadratic. Okay, here comes Huang's breakthrough. What he showed actually is the Fanchong's conjecture. He proved that let H be an arbitrary 2 to the n-1 plus 1 vertex subgraph of the Boolean hypercube, then the max degree is at least root n. As a corollary, that means the sensitivity complexity is always larger or equal the square root of the degree. And using the fact that degree is larger or equal to the square root of BS, this also implies that the block sensitivity is upper bounded by SF to the 4th power. Due to the time limit, I will only give a sketch of Huang's proof. So the key point is that he used a tools, the Cauchy-Interlace theorem. Basically, he constructs a matrix A tilde. It's a relax of the adjacent matrix. And he can show that this matrix, the eigenvalue, the 2 to the n-1 eigenvalue, largest eigenvalue, is still root n. And using the Cauchy-Interlace theorem, then he can show that for subgraph with more than 2 to the n-1 vertices, the maximum degree is at least this eigenvalue, is at least root n. Okay, so the open problem. Although the sensitivity conjecture is proved, but the gap between BS and SF, still there's some gap there. Huang shows that BS is upper bounded by the 4th power of sensitivity times some constant. And the best known lower bound, as I said, is quadratic. So can we prove or disprove that BS is upper bounded by square of S sensitivity? Or even a stronger version of this is it possible that block sensitivity upper bounded by S0 times S1 up to some constant? Actually, a refinement of Huang's proof actually gives that the degree is upper bounded by this product. Also, can we improve the gap between design complexity and sensitivity? The largest gap we know is cubic, and Huang's result only imply a 6 power upper bound. Another direction for sensitivity is to study the sensitivity complexity for special functions, for example, the weakly symmetric function. Actually, in 1984, Tulan already conjectured that for any non-trivial graph property, the sensitivity is at least m at 1. In the same paper, he showed a lower bound like n over 4. And the question here is improve the factor from 1 over 4 to 1. And in 2017, Babel extends this conjecture to hypergraph. He conjectures that for K-uniform hypergraph, the sensitivity is at least n to the k over 2. So if we use the capital N as the order input and choose k, then this is square root of capital N. Together with Qian Li, we disprove this conjecture by showing that there exists a graph property. The sensitivity is only n to the k over 3. Roughly, there's a ceiling function there. And actually, in 2004, Chakrabarty already conjectured this for weakly symmetric function. He conjectures that the sensitivity for any weakly symmetric function, the sensitivity is at least n to the 1/3. Okay. And I was able to prove this for block sensitivity. But still, for sensitivity, even we use Huang's result, it only gives n over 12 upper bound. There's still a large gap there. As we already see, the polynomial degree play an important role in Huang's proof. So let's move to the last topics, the polynomial degree part. I already defined the polynomial degree over real, but we can also define it over the ZL, the modular ring. Okay, it's the multilinear polynomial represents the function over the ring ZL. And since some coefficient of the real polynomial may be vanished in ZL, therefore the degree is always larger than or no more than the degree m. And the gap between them could be very large. For example, consider the parity function. The degree, of course, is n, and the degree 2 is only 1, because it can be written as the summation of all xi modulo 2. And not only for 2, but for any prime or even prime power, the degree p to the k can be a constant. This follows from the Fermat-Little theorem. We can construct a function. It's non-degenerate. So a natural question is, what's the largest gap between degree and degree pq? A composite number, p times q. Because for prime or prime power, the gap can be arbitrarily large. Here is an important proposition here. So by the Chinese tremendous theorem, the degree pq actually is the maximum degree of degree p and degree q. Therefore, if the gap between degree pq is not that large, that means at least one of them is large. Okay, this was conjectured by Goplan et al. In 2010. They conject that the largest gap between degree and degree PQ is polynomial. And in the same paper, they prove the following lower bound. For any non-degenerate function, the degree Q basically is at least n divided by p to the degree p. For example, we know that degree 2 of parity function is 1. And from this theorem, we will know that the degree 3 for parity function is omega n. That means if one of them, degree p, is small, then degree q must be very large. And if we do a trade-off, this theorem gives a basically log n lower bound for degree pq, or log degree lower bound. So that means the gap between degree and degree PQ is at most exponential. However, the conjecture states that the gap is at most polynomial. And together with Qian Li, we show that there exists some function such that the degree is omega n, but the degree PQ is only root n. That means if the conjecture is true, then the constant in the exponent is at least 2. We also prove several equivalent conjectures of this conjecture by replacing the degree with some different descentry measures like sensitivity, like rank P. And these measures relatively smaller than the degree in some sense. Here's a remark. Okay, the sensitivity part now can directly follows from Huang's result because degree is upper bounded by a sensitivity square. But notice that our result is in 2017. At that time, we still don't know. The largest gap is still exponential. Okay. And since we cannot prove this conjecture for general function, the gap is exponential. So can we prove it for special functions? For example, for symmetric function. Since for symmetric function, we know the degree is always n, omega n. So the only thing is to show a lower bound for the modular degree of symmetric function, or equivalent. How low can the modular degree for a symmetric function? As I said, using Fermat-Little theorem, we can construct a function which is symmetric, and the degree p to the k is very small. And together with Qian Li, we show that for any non-degenerate symmetric function, p times degree p plus q times degree q is at least n. Therefore, this gives a lower bound n over p plus k. That means for constant p and q, the degree pq is omega n. And very recently, together with Yuan Sun, Jiaheng Wang, Kewen Wu, Zhiyu Xia, and Yufan Zheng, we further improve this bound to n over 2 plus 1 over k minus 1 plus 1 over q minus 1. By the way, Kewen will give the next talk after me. Okay, open problems. So for symmetric function, when the Gather and Roach actually conjecture that the degree, not only omega n, but n minus some constant. So far, the best known lower bound is n minus n to the 0.54. The 0.54 comes from the largest gap between primes. And another conjecture is, can we improve the lower bound for modular degree to n over 2? So in the paper I mentioned before, we also give an upper bound. It's roughly 1/2 n plus some little term. And also the biggest open problem, the Goplan et al.'s conjecture is still there. And even stronger version of this conjecture can be proved that degree is upper bounded by the square of the degree PQ, or even degree P times degree Q. We still don't know the answer. Okay, that's all I want to say. Thank you for your attention.
Now we have some question from the audience. One question is, you have mentioned that some recent results in the area are based on Huang's breakthrough. Did they only use the result by Huang, or is it possible to utilize Huang's technique, not just his result, to tackle other open problems in Boolean function complexity?
Yeah, this is a wonderful question. Actually, many people try to thinking in this way, and well, the quantum adversary method, I mean the quantum adversary conjecture, is just one direction and one result. And I think still a lot of effort is made to try to get more result from Huang's breakthrough and Huang's technique. So basically, the proof is use a nice measure defined by Huang, the lambda of that extension adjacent matrix. So people are trying to think about whether we can use it to other problems. That's what I know so far. Thanks.
Okay. Thank you. Yeah, we don't have any other questions. Thank you. Let's thank the speaker and Xiaoming. And we have the next session at 10 a.m. Thank you.
Okay, thank you.
Yeah.
Thanks.
So you take over after at 10.
Okay, sure.